All right, let's do some examples. A sample was obtained of times of sleep for normally distributed, randomly selected adult subjects included in the National Health and Nutrition Examination Study. Those times are listed below in hours. A common recommendation is that adults should sleep between 7 hours and 9 hours each night. Using a 0.05 significance level, test the claim that the mean amount of sleep for adults is less than 7 hours. The first thing we're going to do is check our requirements. We have two requirements. The first one is that we have a simple random sample. So is the sample a simple random sample? Yes, we have that right here, randomly selected adult subjects. And then the second requirement is that either the population is normally distributed or the sample size is greater than 30. We definitely don't have n greater than 30. Here we have n is 12. But we do have normally distributed. So since we have normally distributed, we have satisfied both of our requirements. Okay, now we can move into the hypothesis test. So state the hypotheses and identify the claim. We always have two hypotheses, the null and the alternative. Sometimes the alternative can be written with a capital A as a subscript of the H instead of a 1. It does not matter to me which one you want to use. Alternative can either be HA or H1. Unfortunately, there's not really a standard convention. Both are used. So for the null hypothesis is always equality. Always equality. And we are hypothesizing about the mean. So I'm going to use mu for my values here. And I want to test the claim that the mean amount of sleep for adults is less than 7 hours. So less than 7 hours. Well, the mean and the 7 are going to repeat. The only thing that's different between the hypotheses is the symbol in the middle. Equality for the null, and then an inequality for the alternative, and that inequality determines what type of test we're doing. A left-tailed test, a right-tailed test, or a two-tailed test. And so I see that I have this word claim here. The claim is that the average is less than 7 hours. So I'm going to label my claim as the alternative. It is important that you label and identify the claim, because when you make a conclusion on a hypothesis test, you are always making a conclusion about the claim, not about the hypotheses. What was the claim? Your hypothesis test goes through with the assumption that the null hypothesis is always true, and then you either find evidence that that can't be the case, your test statistic ends up in a rejection region, or you have evidence that doesn't refute the null hypothesis, which means it lands in a non-rejection region. Okay, well, let's see what this one does. So there are first two big pieces. State the hypotheses, identify the claim. Don't forget to identify the claim. That's important. And then next, find the critical value. So with the rest of the steps, critical value, the test value, or p-value make the decision. Step 2, 3, and 4, we're going to look at the template for this. You can do it by hand if you want to. The calculation isn't bad. It's just a lot of arithmetic. And for us, I don't want us to focus on the arithmetic part. I want us to focus on the interpretation part, which is why we're using the template. We're hypothesis testing for one mean. I have up at the top hypothesis testing for one mean. There's my mean, and I can choose greater than, not equal to, or less than. My alternative is less than, so I'm going to keep it at less than. But notice my alternative is less than 7, so I'm going to change that 60 to a 7. I do not know the population standard deviation. I do not know the population size. In my class, you will never know the population size, but it's very rare that you know the population size. I'm going to delete the values here because we have the raw data. And since we have the raw data, we're just going to put in the raw data. So I'll type these in. And notice, since you provided raw data, the template computes the sample mean, sample standard deviation, and finds our sample size n, and we have those values here. It gives us our critical t value, except alpha. Oh, I need to change my alpha. Here I have alpha is 0.1. I need a 0.05 alpha. So I'm going to make that change. So 0.05 alpha, and my critical t-value changed to negative 1.79588, so 1.796 is my critical value. And then the calculations in gray, these are all ancillary calculations. You don't have to worry too much about them. And then here's our test statistic, and then our p-value. And it does give us a conclusion. But again, those are the things that I want you to pull from the template. Let's plop them over here on our notes and talk through what they all mean. So the critical value is this t negative 1.795. So critical value 1.796. I'm going to draw my t distribution here. I've got negative 1.796 here, and then on the left is 0.05 area. So when I'm looking at this graph, separating it into two different pieces, I have the rejection region on the left, and I have the non-rejection region on the right. Flip back to my template. The other two values that I need, I have the critical value here, the t-SAM, t-score of sample mean, this one right above the p-value. This is my critical value. Negative 0.2897. So the test value, t negative 0.2897, 2898. And the template gives us our p-value as well. So the p-value and the test statistic are related to each other. And remember, I told you could do either the traditional method, which is compare the test value to the critical value, or do the p-value method where you compare the p-value to the alpha. And we'll talk through both of them to talk about why. And then p-value is 0.389. And if we're talking about percentages, notice this is 38.9%. It's a pretty high p-value. Once we have the test statistic and the critical value, we can do the traditional method, which I will do here in red. So traditional method means compare the critical value and the test statistic, or the test value. So my test statistic, negative 0.2898. If I'm on this number line here, I have negative 1.7 and 0. Negative 0.2 is going to come between 0 and negative 1.796. It's closer to 0. Since my test statistic ends up in the non-rejection region, we do not reject the null hypothesis. When we work through a hypothesis test, when we calculate this test statistic, when you look at the formula, you are assuming the mean is 7. The value of the population mean is 7. You assume the population mean is 7, calculate this test statistic using the values, and then if your calculation of the test statistic lands in the non-rejection region, then that means that the value of your mean being 7 isn't a bad guess. So we don't want to reject the null. Let's do a really quick check, and sure enough our template says do not reject null hypothesis. Okay, p-value method. For the p-value method, we don't necessarily need the graph that's above. I like the graph because I like to compare numbers on a number line. It helps me as a visual learner see what's going on and see where my test statistic is falling. For the p-value method, you're comparing the p-value to alpha. So my p-value is 0.389 and alpha is 0.05. If we're doing a two-tailed test, our p-value would be different, so we need to be careful when we're doing these. So this is a one-tailed test, so our p-value is just the value. If we're doing a two-tailed test, we have to double the p-value. But that comes in the template. The template will already do that. Okay, so p-value method. You can think of this p-value as a probability because that's what it is. So I'm going to read a formal definition and then I'm going to try to break it down. A p-value is the probability of obtaining test results at least as extreme as the results observed under the assumption that the null hypothesis is correct. So we assume the null hypothesis is correct. We're finding a probability that I'm obtaining test results similar to my sample, at least as extreme as what I actually observed. Now this probability, 0.389, that's a high probability. That means it's very likely that we would get similar samples to what we already had. That also means that since the p-value is greater than my significance level, we would not reject the null. So the idea being, if your p-value is smaller than alpha, that means the probability of getting the test statistic with another sample is really small. If that probability is really small, then it's very unlikely that the null hypothesis is true. But notice, we get the same result. Whether we do the p-value method or the traditional method, we're going to get the same conclusion. That's important. What it really also boils down to is this p-value here, this 0.389 that shows up for our p-value, is actually the area that the test statistic gets. So I'm going to erase what I just did so we don't get too cluttered on that graph. But this 0.389 here, negative 0.289, the p-value is the area that the test statistic is going to give me. They're directly related to each other. And that's why we can use either of them and they'll give us the same result. Okay, make the decision. Well, we already made it twice, but let's write it out over here. Do not reject the null. And then we summarize the results in context of the problem. Yes, you need a summary. You cannot just end a hypothesis test with do not reject the null. You have to tell me what that means in terms of the claim that you provided at the beginning. So we have to come full circle. Let's go back up and look at our hypotheses. We did not reject the null, which means we don't have evidence to support this claim. The conclusion is what gets a little tricky because of the wording. And I know I walked through it in a previous lesson, but now that we have a solid example, we are not rejecting the null, which means the null is staying. It's still valid. That means we cannot say that the claim is true. So there's not enough evidence to support that claim. And that's how we're going to write the summary. We would say there's not enough evidence to support the claim. And we're going to repeat the claim that was given. The mean amount of sleep for adults is less than 7 hours. And there's our hypothesis test.